The Archimedes screw, one of the oldest machines still in use today, is a fascinating example of ancient engineering ingenuity that has stood the test of time. Named after the ancient Greek mathematician and engineer Archimedes of Syracuse, this device was reportedly invented during his visit to Egypt around the 3rd century BCE. Historically, the Archimedes screw was originally designed for irrigating fields and removing bilge water from ships, serving as a practical solution to lift water to higher elevations. The basic principle of the screw, a helical surface surrounding a cylindrical shaft, allowed it to draw water upwards efficiently when rotated, exploiting the mechanical advantages of the inclined plane in a compact, rotating form. Components of Archimedes screw include the helical screw, the primary component that initiates motion. The screw acts as a continuous inclined plane wrapped around a central axis. Its primary function is to convert rotational movement into linear vertical motion. This conversion is fundamental to understanding how the screw operates as an efficient mechanical device. Coexistence is key in the operation of the Archimedes screw. Each component, including the screw, the cylinder, and the water, must interact simultaneously for the device to function. This highlights a symbiotic relationship where the absence of one component would render the device non-operational. The design of the screw and the structure of the cylinder directly impact how effectively water can be lifted, underscoring the necessity of each component's presence and correct interaction for the device to operate. Reinforcement is crucial. The rotation of the screw, caused by an external force, typically human or motor-driven, moves the water along the cylinder. This sequence not only transfers mechanical energy through the components, but also emphasizes the need for each component to effectively support the next, reinforcing the overall operation of the device. The screw's rotation, aided by its helical structure, an inclined plane, efficiently moves the water upward. The cylinder supports this movement by confining the water to the path of the screw's threads, reinforcing the efficiency of water transfer from the lower end to the discharge point at the top. The causal relationship in the design of the Archimedes screw is primarily dependent on the action of the helical screw. Its rotation is a direct cause for water movement, and without it, the operation ceases, demonstrating a clear chain of effect from initiation to outcome. In Archimedes screw, several forces interact to enable the efficient movement of water. First, we have the rotational force. This is the external force applied to the screw, typically by hand or motor, which initiates the rotation of the screw. It is the starting point of the energy conversion process from rotational to linear movement. Next, the lifting force comes into play. Generated by the rotational motion of the inclined plane of the screw, this force directly translates into the upward movement of the water against gravity. This is a critical aspect as it represents the primary purpose of the screw, moving water vertically. Finally, we encounter the resistance force. This encompasses the forces opposing the lifting force, primarily gravity pulling the water downwards and friction between the water and the internal surfaces of the screw and cylinder. This force must be overcome by the lifting force for the water to ascend effectively. Coexistence. These forces are all present and actively interacting throughout the operation of the screw. The coexistence of these forces determines the efficiency and effectiveness of the device, with each force needing to be balanced against the others. Reinforcement. The rotational force leads to the lifting force, which must overcome the resistance force. This sequence shows a continual feedback loop where the resistance, including friction and gravity, dictates the amount of rotational force needed, which in turn defines the magnitude of the lifting force. Causal. The presence and magnitude of the rotational force directly cause the lifting force to act. Without rotational force, there would be no lifting force, thus highlighting a direct causal relationship where the initiation of one force is essential for the existence of the other. Insights. The analysis of both the physical components and the forces at play within the Archimedes screw through triadic relationships provides a comprehensive understanding of its mechanics. The relationships among components and forces are both reinforcing and causal, suggesting a highly interconnected and dependent system. The main objects, helical screw, cylinder, water, and main forces, rotational, lifting, resistance, are identified through their interactions, establishing a model that can potentially guide the design improvements or applications of similar mechanical systems. Throughout the centuries, the Archimedes screw has been adapted for a wide range of applications, from irrigation and water management to modern uses in wastewater treatment plants and even hydroelectric systems. Its enduring utility lies in its simplicity, efficiency, and the ability to operate under a variety of conditions with minimal maintenance. This device not only illustrates the genius of ancient engineering, but also highlights a continuity of technological evolution, connecting past innovations with present-day solutions. This model serves not only to understand the existing design, but also to foresee how changes in any one of the elements or forces could impact the overall functionality and efficiency of the device, guiding future innovations and optimizations.